Here are two reasonable answers to the same Calculus 1 question. What the question is isn't super relevant right now. What is relevant is that for the question I have in mind, this answer would receive full credit, x squared plus c, whereas for this answer, the student would probably lose at least 1 point, if not more. And indeed, many calculus students will lose far more points than they would like to admit to this simple mistake. Today, I want to give you an accessible explanation of what this mistake is, why it's so easily made, and why it is significant, and you deserve to lose a point if you make it. For those who have taken calculus, this may bring back some vivid and unpleasant memories, and for those of you who don't yet know calculus, I hope you'll find it really interesting. To understand the graveness of this infuriating calculus error, it's important to understand some basics about the two big ideas introduced in Calculus 1, the idea of the derivative and the integral. Let's start with the derivative. The derivative of a function f of x is typically denoted like this, f prime of x, and it gives the slopes of the lines tangent to f of x. You can think of a tangent line as a line that has the same direction as the function at a particular point. For example, here's a graph of a cute little function we might call f of x. Again, a tangent line is a thing that exists at a point. So this function has a tangent line at this point, but it also has a different tangent line at this point over here. To picture a line which has the direction of the function at a particular point, imagine a point moving along this curve like it were a track in two-dimensional space. Now, as that point moves along the track, suppose the track disappears right here, so now there's nothing else to influence the point's direction, and it would just veer off in whatever direction it had when the track vanished. That gives you an idea of what the tangent line would look like at this point, and we could sketch it as looking something like that. Again, it's a line which goes in the direction of the function at this particular point. Since the function was sloping upwards at that point, the line has a positive slope, and the slope of the line is the derivative of the function at this particular point. So at this particular point, we might write that f prime is greater than 0. The slope of the tangent line here is positive. On the other hand, we could imagine the point traveling along this track until we get here. Then the track disappears and the point continues in whatever direction it had. That again gives us an idea of what the tangent line looks like. And we could quickly sketch it. It looks something like that. At this point, the function is going down, and so the slope of the tangent line is negative, and we could say then that the derivative f prime is negative. Understand from this discussion that the derivative is itself a function, which takes on different values at different points. Over here, the derivative was positive, but over here it happened to be negative. Of course, the definition of the derivative is more rigorous than the brief explanation I've given here. And using the rigorous limit definition of the derivative, a student in Calculus 1 will establish a variety of useful rules for finding derivatives of familiar functions. For some examples, the derivative of the function x squared is 2 times x. This is a particular example of what's called the power rule. We can find the derivative of x squared by taking the power of 2, bringing it in front as a factor, and then reducing the power of 2 by 1. So the power in the derivative becomes 2 minus 1, which is just 1. We can apply that rule also to find the derivative of a function like x cubed. Bring the power of 3 down as a factor, and reduce the power by 1. The derivative is 3x squared. The natural log function is something you might be familiar with if you've taken pre-calculus. The derivative of this is 1 over x. Remember that the derivative of a function gives the slopes of the tangent lines. In the case of a linear function like m times x, the derivative will just give that fixed slope of m at every single point. And in the case of a constant value like 5, well, if we graph that, it's just a horizontal line. It's flat. Its slope, and thus its derivative, is 0. More generally, the derivative of any constant fixed value is simply 0. Again, that's because when we graph a fixed value, whether it be 5 or any other constant, it is just a horizontal line in the plane. It doesn't go up, it doesn't go down. Its slope is 0. It's also straightforward to find the derivative of multiple functions added together. If we take x squared plus a constant, for example, its derivative is just the derivative of x squared plus the derivative of the constant, so it would just be 2x plus 0, or just 2x. More generally, the derivative of any function f of x plus an arbitrary constant would just be the derivative of that function f, so that would be f prime, plus the derivative of the constant, which is 0. This prime notation is very common for derivatives, but often we would say that the derivative of a function big F is denoted little f. That's just a matter of notational convenience. That's a small list of some basic derivatives. Notice how this all goes in one direction. Here's a function, here's its derivative. Here's a function, here's its derivative. But it is also sometimes necessary to go the opposite direction, to take an antiderivative. An antiderivative is exactly what it sounds like. So an antiderivative of 2x, for example, is x squared, because the derivative of x squared is 2x. That means x squared is an antiderivative of 2x. Similarly, we may ask what function has a derivative of 3x squared. Since x cubed has a derivative of 3x squared, x cubed is an antiderivative of 3x squared, and we could fill the rest of this list out similarly. And that gives us this small list of antiderivatives. Now you may be paying special attention to the c's, since they appeared in the beginning example. And now we can start to see the importance of these fixed constants. An antiderivative of 0 is 5, but that's not the only antiderivative of 0, because indeed any constant value would have a derivative of 0. Similarly, x squared is an antiderivative of 2x, but more generally, any function of the form x squared plus c is an antiderivative of 2x. We certainly need the x squared there, so the derivative gives us 2x, but we'd also be free to add any constant we like, and the derivative would still just be 2x. And this should make perfect sense. X squared, we know, is a parabola, and remember, the derivative gives us the slopes of the tangent lines. When we add some fixed value to x squared, that doesn't change the slopes of the graph. It still has the exact same shape. All it does is moves it down or up, depending on whether c is negative or positive. So of course, an antiderivative of a function little f of x could be big F of x plus any arbitrary constant. All on its own, these ideas are not too complicated. If you're just asked to give an antiderivative of 2x, x squared is a perfectly valid solution. But if you're asked to give the general antiderivative of 2x, you'd have to say x squared plus c, since any function of this general form is an antiderivative of 2x. Despite this, calculus students will so often forget this plus c when it's needed, because this isn't typically how the question is presented. They're not asked for a general antiderivative, but that's instead wrapped up in some potentially confusing notation. To explain this, we need to briefly look at the other half of calculus, called the integral calculus. Here's a snapshot of a cute little function we will, for convenience, call f of x. Let's say that over here is the horizontal position x equals a, and over here is x equals b. Then, a question we might ask, which is entirely unrelated to derivatives, is what's the area underneath this curve from x equals a to x equals b? By underneath the curve, we mean between the curve and the x-axis, the area which I'm shading here. This is a peculiar shape, so it's not obvious how we would find this area. Regardless, it's called the integral of the function from a to b, denoted like so. The beautiful integral sign tells us we want the area underneath this function, f of x, and the dx tells us that it's x going from a to b. We're moving from this lower bound horizontally to that upper bound. Sometimes an integral is pretty easy to evaluate. For example, it's quite easy to find the area underneath lines. Perhaps this is the function f of x equals 2x for x greater than 0. And perhaps over here is the horizontal position x equals 2. Then, finding this area underneath the line from x equals 0 to x equals 2 is as easy as finding the area of a right-angled triangle. So in this example, we could say that the integral of f of x, which is 2x, as x goes from 0 to 2, this integral, which is the area of the right-angled triangle, is 1/2 times base, the base is 2, multiplied by the height. The height of the triangle is the distance from here to here. Since the function is 2x, the y value here is 2 times 2, or 4, so the height is 4. Thus, the area we're looking for is equal to 4. In general, though, it is not so easy to use elementary geometry to evaluate integrals. For example, just consider the very common and otherwise simple function f of x equals x squared, graphed here for x greater than 0. Finding an integral of x squared would involve finding the area of one of these oddly shaped regions underneath the curve. This is not something that our elementary geometry can handle. Indeed, if we call this the horizontal position x equals a, it's not at all obvious how we should evaluate the integral of x squared from 0 to a, or if in fact this is even going to be possible. As it turns out, we actually can use elementary geometry in combination with what's called a limit to evaluate this area by splitting it up into a bunch of tiny rectangles and looking at what happens as we split it up into more and more rectangles. Finding the area of a rectangle is easy, so then the difficulty just becomes letting the number of rectangles get bigger and bigger so that the error in our calculation approaches 0. However, that's pretty tricky, and there's a far more powerful and easy to use tool that calculus students come to rely on, and that's the fundamental theorem of calculus. And here's that theorem, stated in two parts as is typical. The first part is very interesting, but it's really the second part that's relevant for us. This establishes a very surprising connection, which in fact makes it really easy to evaluate integrals like this. It says if we want to find the area underneath a function f of x from x equals a to x equals b, all we need to do is find an antiderivative of that function f of x, evaluate the antiderivative at the upper bound b and the lower bound a, and just subtract those values. And notice here how it says big F can be any antiderivative of little f, the function we are integrating. So if we want to find the area underneath x squared from x equals 0 to x equals a, we really just need to find an antiderivative of x squared. Now, if you remember the power rule we described earlier, how to take the derivative of x cubed, for example, we bring that power of 3 down as a factor, and then reduce it by 1 to get a new power of 2, then it shouldn't be too difficult to figure out an antiderivative of x squared. Adding this to our list of antiderivatives, an antiderivative of x squared, well, it would need a power of 3, so that the power gets reduced by 1 to become 2, but the derivative of x cubed would involve bringing that 3 down as a factor, and of course x squared doesn't have that factor of 3, so we would need to put a 1/3 in front of this to cancel out that factor of 3. If we take the derivative of 1/3 x cubed using the power rule, we get x squared. Now, this is a particular antiderivative of x squared. We could add plus c just to represent a general antiderivative. Any antiderivative of x squared has to look like this, 1/3 x cubed plus some constant. We could then use this antiderivative to evaluate this integral. And this should feel like a magic trick. Again, this is part 2 of the fundamental theorem of calculus we're using. This has established a connection between two things which we had no reason to believe at first were connected: the area underneath a function and its antiderivative. So to evaluate this integral, all we have to do is take the antiderivative of x squared, which we just discussed is 1/3 x cubed plus c, evaluate it at a, evaluate it at 0, and subtract. This is the notation that's often used for that. This says we're going to evaluate this expression at x equals 0, evaluate at x equals a, and then subtract the lower one from the upper one. This is a pretty straightforward process. We have 1/3 plug a in for x, so 1/3 a cubed plus that constant c, and then subtract plugging in the lower bound, which is 0. That's going to be 1/3 0 cubed, which is just 0, so all that's left then really is that constant c. Now you can see how the constants cancel out. This is why the fundamental theorem says we can actually use any antiderivative of the function being integrated. The only thing that could be different between two antiderivatives is this constant. But at the end of the day, when you do this subtraction, those constants will cancel out. Thus, any antiderivative will yield the same value for the integral. In this case, canceling out those c's, we get a final answer of 1/3 a cubed, which is, if you haven't seen it before, a pretty surprisingly simple formula for the area underneath a parabola from x equals 0 to x equals a. So the incredible trick we've seen here from the fundamental theorem of calculus is that an integral can be evaluated using antiderivatives. This is the reason behind the double use of the integral notation, which is part of what contributes to students' mistakes. As we originally described the integral, it would have no meaning without a lower bound and an upper bound telling us where we are looking for the area, from where to where. However, because of the intimate connection between integrals and antiderivatives as established by the fundamental theorem of calculus, an integral sign with no bounds is called an indefinite integral. There are no bounds giving it a definite value, and it is instead used to represent the general antiderivative of the integrand. So if we write this integral symbol with no bounds, and then x squared dx, this is representing the general antiderivative of x squared. That's just how the notation is used. And we know that's 1/3 x cubed plus c. We already discussed that. You can then begin to see why the mistake of not including the plus c is so easy for students to make. The integral symbol is typically first used for definite integrals, and that's where it originally comes from. And because when evaluating a definite integral using the fundamental theorem of calculus, when we do that, this arbitrary constant cancels out, we don't actually write the arbitrary constant when doing a definite integral. For a quick worked out example, if we were asked to find the integral of 2x from x equals 0 to x equals 5, we can use the fundamental theorem of calculus and the fact that we know x squared is an antiderivative of 2x. It's not the general antiderivative, but we don't need that for the definite integral. We would just write that this is equal to x squared evaluated from 0 to 5, and then plug in 5, 5 squared is 25, minus plug in 0, 0 squared is 0, we would get a final answer of 25. We never ever have to consider a plus c for evaluating this integral. Again, we could write it if we wanted to, but it wouldn't make our answer any different, it wouldn't make our solution any more correct. By the fundamental theorem of calculus, any antiderivative suffices for evaluating a definite integral. This then builds a habit of not including the c, and more specifically, not connecting this symbol with that arbitrary plus c constant. The student gets it ingrained in their mind that the plus c doesn't do anything. It cancels out at the end of the day, so it's not necessary. The issue is that this same symbol, the integral symbol, is used for an entirely different request, which happens to be intimately related. When we look at this, an integral with no bounds, an indefinite integral, this has nothing to do with area. This has nothing to do with the fundamental theorem of calculus. It's just asking us what the general antiderivative of x squared is, and that's 1/3 x cubed plus c. Just as another example, going back to our list of antiderivatives, the general antiderivative of 2x is x squared plus c, so we could write the indefinite integral of 2x with respect to x is x squared plus c. So why do calculus teachers so mercilessly strip away your points for this mistake? Well, for one, it's genuinely not a correct answer. X squared is an antiderivative of 2x, but it's not the general antiderivative, and if you're asked to evaluate this is asking for the general antiderivative. The only correct answer is x squared plus c. It's possible you know exactly what this means. You know the plus c should be there, and you just forgot. The more unfortunate possibility, which I think is why teachers have to punish this mistake, is that it conveys a misunderstanding of the notation. And while it's possible you don't misunderstand the notation and you just forgot, there's no way for the teacher to know. This is not asking for an antiderivative that can be used to evaluate areas underneath the function. For that, x squared works fine. Again, it's asking for the general antiderivative, and for that, you need x squared plus c. Any antiderivative of 2x has this form. The integral symbol is a piece of notation that's used for two different things that happen to be intimately connected. In a Calc 1 class, you'll learn more about this deep connection and why it must be true. Certainly, I think calculus is one of the most impressive and beautiful intellectual achievements of our species, so I'd really encourage you to take a course in calculus if you have the chance. Anyways, please let me know in the comments if you have any questions or if you have any fun experiences to share with calculus class and perhaps making the infamous plus C mistake. Thank you very much for watching, and be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and unsort the cable. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.
Faded.